host you, and in NYCU. This is a special lecture on the purpose of general audience, liberal and arts, and this is very much highlighted after the merger of Yangmin with Chiao Tung in year 2021. So we are a university of 3 years of age, but this is a merger from two outstanding universities of long history. Yeah. So again, welcome you. So I don't want to occupy too much time. So just on behalf of the university, I send my warmest regards and also our appreciation for you to really share with you your wonderful exploration, not only the universe, as you were mentioned, as you were lecture about, but also your life. Thank you.
Thanks to our Principal Lin for his talk. Next, let's invite our Professor Yang Yi from the Faculty of Science for the speaker introduction. 谢谢校长的致辞。在精彩的讲座开始前，我们有请理学院电子物理系杨毅教授为我们带来讲者介绍。
OK， 大家好，我想大家都非常期待今天诺贝尔得主田龙章教授来这边讲座。不过我们今天因为来的人各路人都有，我们有教授，有研究所的学生，有大学部学生，甚至还有高中生，然后领域也不都是物理领域，所以我先在这边给大家做一个简短的介绍一下尾田龙章教授的一些成就，还有他的研究领域。那为了让大家可以更了解，所以我用中文给大家介绍。OK， 所以我先介绍一下尾田龙章教授的经历。他1986年是东京大学博士毕业。1986年我应该还在上小学啊，在位很多人可能还没有出生。然后1992年他又拿到了东京大学宇宙射线研究所的助教授，相当于我们的助理教授。然后1996年就成为宇宙射线研究所的教授。然后由于他的研究成果非常多，所以2016年东京大学授予他特别荣誉教授。然后接着又在2017年东京大学授予他卓越教授。那这是在东京大学非常最高 class 的奖励。那现任尾田龙章教授是东京大学宇宙射线研究所的所长，也是东京大学国际高等研究所的主任，还有日本学术会议的会长。当然我们很重要的也是日本重力波探测器 KAGWA 的总主持人，这个我们一会儿还会再提一下。尾田龙章教授获奖无数啊，这边我只是列举出一些比较重要的奖项，比如布鲁诺·罗西奖，这个是美国发的高能天体物理奖；那朝日奖是日本的杰出科学家；仁科方雄纪念奖是日本最高的科学奖，基本上日本上所有的功成名就的日本科学家都拿过这个仁科方雄奖。然后这个潘诺夫斯基实验物理奖也是美国的奖项。然后还有个日本学士院奖，这是不分理科学科的日本的一个最高奖项。那当然最重要的诺贝尔物理奖，这个是全世界最高 class 奖，我想大家都知道。那还有一个是最近的一个物理奖，是2016年拿到基础物理学突破奖，这个是在基础物理里面非常有重大成就才会颁的奖，得到人其实到现在为止并不多。我想给大家稍微介绍一下尾田龙章的主要研究成就。他主要研究成就是在微中子方面，当然他有两个，一个是微中子，一个重力波。那得诺贝尔奖的原因是微中子，所以我稍微介绍一下微中子，可能不是所有人都清楚哈。微中子是从原子衰变，这个大家可能知道，原子核会衰变，衰变 其中一个我们叫贝塔衰变，会往外发射一个电子。那这个很早就知道了，100多年前就知道了，所以大家对这个研究了很多，做很精密的测量。测量以后就发现这个过程能量不守恒。那当然，能量守恒我们知道是我们整个宇宙里面一个非常非常重要的事情，所以不守恒就坏事了。所以一定要守恒。那怎么解决这个问题？那这个问题是由非常著名的物理学家 Pauli 他提出了一个假想，他说不守恒是原因，这个过程中还有另外一个粒子，那他管它命名叫微中子。这个粒子他当时猜测是没有电荷也没有质量的一个粒子，所以这个粒子会带走一定的能量，但是这个粒子在当时的技术你又测不到，所以你测量你只能看到这个电子，看不到这个微中子，所以当然你测出来的这个能量就不会守恒，所以他用这个方式去解释。当然这是个理论解释，任何理论解释都要有实验的支持才可以。但是这个微中子非常的难测量，微中子和其他物体的相互作用很小。我们想测量一个物体，我们基本上要测量它的反射，比如我们看光，我们是光打在这个物体上反射过来，我们才能看到。那微中子也一样，它必须和其他物体有相互作用，你才可以看到它。可是微中子跟其他物体的相互作用非常非常的少。地球对于微中子来说几乎都是透明的，也就是微中子穿过地球可以毫无障碍的把整个地球穿过，但几乎啊，如果真的完全穿过，我们就测不到了。它几乎可以完全穿过，只有很少量的微中子可以留下来。所以这个使得微中子的测量在当时那个年代，在泡利刚提出来的年代是基本上不可以测量的，不可能。那后来大家做了很多努力。那右边这个图就告诉大家，微中子测量的人和一般的这个天体物理学家有什么不一样？一般的这个做天体实验是都往山上走，大家应该都知道哈，越往山上走噪音越小，甚至我发卫星，在卫星上是噪音最小。但是做这个微中子的，它是往地下挖，原因是我挖到地底下，我上面的这个地球这些层就会把其他的所有粒子全都屏蔽掉，只有微中子可以穿透下来，所以我在地底下反而看的这个 source 看的所有的东西通通都是微中子，所以我们的微中子探测器都是往地下挖的，都是跟这个普通的天是完全两回事。那它非常的困难，经过了几十年的测量，第一次在1956年发现了微中子，那也是这个 Reines 美国的物理学家发现了，他的设备啊就是这么一台设备，当然放到地下去的一个设备，当时现在看起来很简陋哈，微中子的设备都非常的巨大。一会儿可能尾田荣章会讲他的这个在日本那个超级神钢的微中子探测器非常的巨大。那1956年发现微中子，他在1995年就拿到诺贝尔奖，因为微中子是非常非常重要的一个粒子。我们知道发现新粒子拿诺贝尔奖其实并没有很多哈，第一个粒子电子当然拿诺贝尔奖，后来中子有拿过，再一些粒子就拿不到诺贝尔奖了。那微中子拿到，说明微中子在粒子物理里面一个非常重要的地位。当然，这是一旦测到了，大家就开始有希望了哈。在之前，大家觉得这东西不知道什么时候可以测到，一旦测到就有希望，有希望大家就开始去这个持续观测。所以微中子第二次拿诺贝尔奖是在2002年拿到的，那是由这两位，第一个是由日本的科学家这个 Koshiba 在1968年发现了太阳中微子，也就是太阳也是核反应，所以它也会往外发射中微子。那这个微中子在地球上我们可以探测到。那接着，在这个 Ryan Davis 在1987年看到了超新星爆炸。超新星爆炸就是基本上恒星在最后的阶段会塌缩，因为它的某些这个核反应不大对头了，就会塌缩，然后会产生爆炸。那这个爆炸会产生很强烈的一些粒子出来，其中就包括微中子。所以1987年就观察到了超新星的爆炸。那由于这两个观测，使得他们得到了2002年的诺贝尔奖，这是第二次。微中子拿诺贝尔奖。那当然，他们这个观测也提出了一个疑问，就是所谓的微中子失踪。他们观测的这个数量和理论算出来的数量是不一样的。假设理论算出来应该有100颗这个微中子，他们只观察到30几颗，所以有2/3的微中子是不见了。所以在当时很著名的微中子失踪的一个事件。那这件事就是我们今天的主讲得主解决的事情，那就是我们在2015年的诺贝尔奖。那是由这两位，就是卡吉塔桑尾田荣章教授，还有在加拿大的麦克汤纳，他们分别用日本和加拿大两个微中子的探测器来做，发现了所谓的微中子震荡这件事情。所谓微中子震荡，就是微中子实际上不止一种，它有3种。那之前测的只能测到其中一种。那在微中子在传播的过程中，会从一种自动的变成其他2种。那一般的粒子不会，一般粒子电子传播就是传播，它只会撞到什么东西了，它可以 可能会做一些改变。但是微中子自己在真空中传播的时候，它就会从某一种微中子变成另外一种微中子，这是自发的。所以我们这个叫做微中子震荡。那在长途传播以后，本来只有一种微中子，它就会变成其他2种微中子。那在当时的这个设备里是测不到另外2种微中子的，它只能测到其中一种，所以它就会觉得这个粒子数和计算的数量是少了。理论计算告诉我100颗，我只能测到30几颗，实际上另外2种是变成了其他的不同的微中子，而它没有测到而已。那在这个后来的实验，在这个他们就测到了其他2种，所以他们证实了微中子这个震荡，所以也同时解决了这个微中子失踪的问题。当然，他也提出了新问题啊，这个就是科学。科学你每次解决一个旧的问题，就会提出一个新的问题。新的问题就是你要理论解释这个微中子震荡，必须要求这个微中子是有质量的。我们刚才讲过哈，最一开始泡利提出的微中子的预言是没有质量的。那现在如果希望有这个微中子震荡，就一定要有质量。有质量和没有质量在物理学是完全两码事。有质量的物体你可以静止，可以运动，但是你不可以超过光速。没有质量的物体你根本不能静止，就像光一样，你就一直永远以光速运动才行，没有办法静止。所以描述这两类粒子是完全不同的物理。所以一开始的所谓的粒子的标准模型是描述的没有质量的微中子。那后来发现有质量以后，那整个的标准模型都要重写。所以这件事对于物理界当然是非常重要的一件事。因此他们也获得了2015年的诺贝尔奖。这个是关于韦田隆让教授获得诺贝尔奖的部分。那另外一部分也就是韦田隆让教授现在的研究方向。那这个研究方向就是现在炙手可热的天文学里炙手可热的重力波啊。重力波是1915年爱因斯坦在建立了广义相对论，他就提出了物质和时空之间会有关系。你时空中如果真空中有个物质，就会导致它周围的时空弯曲。那当然，导致时空的弯曲，你这些物质会运动。当你这些物质在时空中运动的时候，周围这个时空就会跟着你一起动，就像波浪一样。那这个波浪就会随着时空向外传播，那这个就是重力波。所以1916年的爱因斯坦就预言了重力波，他写了一篇文章。那据说好像当时投出来就被退回来了哈，但是他还是不大相信这件事情。但是也确实这件事是很神奇的一件事情。当时大家不相信是可以理解的，因为1916年预言重力波以后，一直也找不到，找了接近100年，重力波是非常难找的。我们现在给一个现在一般重力波的一个标准的图像，那大家可以看到中间这个蓝色的啊，如果你眼睛还够好的话，你可以看到这个就是一个重力波，一个典型的2个黑洞合并的一个重力波信号。外面这个红色是什么？是噪音。你们在其他的实验里面很难看到这么巨大的噪音的哈。但是这个图是为了让你们可以看到重力波，我故意把重力波放大了。真正的噪音是重力波的1000倍左右，所以大家就可以知道，在这么一个巨大的噪音里面，你想把一个非常非常小的重力波找出来是很困难的一件事情。也就是为什么爱因斯坦提出来以后也没人相信他，因为也测不到，不是说你摆一个东西就可以测到的。虽然我手一挥就可以产生重力波，但这个重力波太小了。我们现在能看到的重力波是什么呢？就现在目前可以看到是2个黑洞旋转产生的重力波，但是2个黑洞旋转产生的重力波还是太弱，我们还是看不到。我们真正看到的是什么呢？前面这是旋转，大家看最右边那一点点，这个是当2个黑洞旋转产生重力波，随着重力波往外发散，它能量会越来越小，能量小，它们就会互相接近，越转越近，最后会撞在一起，合并成一个黑洞。那这个撞击过程会产生一个非常强大的重力波，我们能看到的就是这个重力波。其实我们可以看到，到现在为止，人类目前可以探测到的重力波就是这么一点点，所以大家可以看到重力波有多么的困难。也因此，这个自从爱因斯坦在1916年预言了重力波以后，人类第一次观察到重力波是在2015年，是美国的实验室重力波加速器 LIGO 观测到的。那观测到就是2个黑洞合并的重力波，基本上这2个黑洞会旋转，旋转以后它们会越来越近，最后撞在一起产生一个强烈的重力波，我们可以观测到。也因此得到了2017年的诺贝尔物理奖。这是重力波方面的物理奖。那下面回到这个日本。日本在2010年也是在尾田荣章教授的建议下，就开始进行了重力波探测计划。大家可以想象，刚才我们说了，人类第一次探测到重力波是2015年，所以在那个之前，大家对重力波是不 care 的。大家觉得重力波是什么？重力波根本不是个主要的天文学问题，因为大家测了快100年，测了 2011年已经测了95年了，什么也没看到，所以当然大家对这个东西不会很认真的去对待。但是就在这个时候，这个尾田荣教授他已经在微中子方面取得了巨大成就，可能大部分人就会继续藏在这个领域里面，很舒适的享受着他这个领域权威。但是尾田荣教授在2010年的时候，在还没有看到任何重力波的时候，他就毅然决然地决定改变他的研究题目。可以看到他对研究的领域的方向的科学嗅觉是非常敏觉的。他改变研究题目以后，5年之后就找到了，然后拿诺贝尔奖。现在重力波已经变得非常的火热，所以你还可以赶得上。你如果不是提前就开始做，你是赶不上的。所以2010年开展重力波计划，那是在这个神冈的山里面挖2条隧道啊，这个是示意图啊，把山抛开，里面会有2条各3公里长的隧道。那他测的就是重力波过来以后，会整个地球都会跟着收缩膨胀。那这2条隧道这样互相垂直的隧道也会收缩膨胀。那测量它们之间的关系，你就可以测到这个微小的重力波。那Kagura的总主持人就是尾田荣教授，他本来是这个微中子的总主持人啊，那他后来在2010年的时候转到这个重力波做总主持人。重力波有多重要？为什么现在重力波一出来，其他的这个刚才说了微中子啊，什么伽马射线啊，各种以前早就有的这些宇宙会观测，为什么重力波一出来它变得那么重要？那就是原因是所谓的多心尺天文学造成的。多心尺天文学告诉我们，当我有任何一个天文学现象，它当然不可能只发出一种信号，它可能发射伽马瑞，可能发射 neutrino 就是微中子，也可能有宇宙线，也可能有重力波，它各种各样都会发出来。那这些早晚都会到达地球，但是在所有这些信号里面，第一个到达地球的就是重力波。所以这个就是重力波为什么会重要。所有的信号，因为其他的信号都会跑来跑去或者发射的比较晚，但重力波是你一旦有反应，它立刻发出来了。而且重力波在宇宙中传播，它是时空本身的变化，它不会受任何东西阻挡。你没有任何东西，你说有一片云，你的伽马射线可能被挡到了；你有一些这个星体，你的微中子可能会挡住。但是重力波不会被任何人挡住，它就是从一开始就是义无反顾地奔向地球，所以它第一个会到达地球。到达地球以后，我们在地球测到重力波以后，右边是个时间顺序啊，我们一开始测到重力波，然后会伽马瑞、X 瑞，因为各种其他的信号就来了。那通常我们找到了重力波以后，就会确定方向。确定方向以后，其他就会通知其他所有的天文探测器，那天文探测器会对准这个方向，然后进行后续的测量。这样可以保证同一个天文事件如果发生了，我们可以及时的测量所有它的信息。这就是为什么重力波这么重要，因为它是第一个，它是一个 trigger， 一个最开始的信号。那它要做得多快呢？要做到重力波来了以后2秒之内，你就要确定这个重力波，然后把它发送到全部的这个国际上这些天文台。那他们在后续跟踪，他们后续跟踪一般在比如几个小时到几天就要对准，然后可以后续测1-2个月这样子，这个事件可以得到完整的数据。这个就是重力波为什么这么重要。那我趁这个机会也打个广告哈，我们很多国家都参加了重力波的collaboration， 重力波的合作。台湾是重力波合作一个非常重要的一个国家，是第二大的。那在台湾这些研究团队里，我们交大也在2019年就加入了 Kagura 的合作团队。目前我们交大的研究团队应该可以说是台湾最大的 Kagura 合作团队之一。我很想把之一拿掉啊，但是怕有些人不高兴啊，说个之一，但应该就没有之二了哈。对，所以希望在这边所有对重力波有兴趣的哈，尤其是大学部的学生，还有高中学生，如果你们有兴趣，希望能继续加入这个研究领域，我们都非常欢迎大家以后来到交大，来到我们电物系，加入我们的团队，来共同进行重力波的研究。最后再插个话哈，尾田荣教授他拿到诺贝尔奖以后就变得非常的有名，所以大家见到他以后就去网上去照相就合照。所以在这个宇宙线中心，因为他是宇宙线的所长嘛，大家去了以后都会去照相，所以他也没那么多时间，就专门立了一个看板在这个宇宙线中心。那去年我们去开会的时候，我们几个学生就空去找，好兴奋的去跟这个看板照相。 这位学生也在现场啊，是我们学生。然后照相以后，但是第二天他的必报，我们会有必报这个演讲，他的必报演讲就拿到了博班生部的1等奖。所以最后由尾田荣章教授亲自给他颁奖，终于和真人可以合照了。对，那今天我们非常荣幸，今天我们把真人请到现场了哈。那到底有没有合照的机会？一会儿看大家有没有时间，有没有机缘。好，那我基本上就介绍这么多。那我希望给大家一个基本的介绍，大家可以从中了解一些背景，那可以更容易理解尾田荣章教授一会儿讲的内容。我想大师的演讲，大家一定会从中得到很多启发，对自己的学习和研究有所帮助。好，谢谢大家。
Thanks to Professor Yang for the speaker introduction. Now, let's welcome Professor Takaaki Kajita with the warm applause. 谢谢理学院杨毅教授为我们带来的讲者介绍。现在就让我们以热烈的掌声欢迎尾田荣章教授。
Where test. Yes. This way. Okay. Okay. Thank you. Well, thank you very much for the invitation to this public lecture. Well, it's an honor to speak to you today. So today I'm going to talk about the exploring the universe with neutrinos and gravitational waves. In fact, well, the title is very general, but in fact, I'm going to talk about essentially what I have done and what I am doing now. Okay, so this is the outline. First, I have a brief introduction on the related scientific field. Then I want to discuss neutrinos or neutrino experiments, Kamiokande, super Kamiokande, and hyper Kamiokande. Then I want to discuss gravitational waves. And in particular, I'm going to talk about the Kagura experiment. Okay, introduction. Well, slightly more than 100 years ago, Victor Hess measured the intensity of radiation at the balloon altitude. Surprisingly, the intensity of the radiation at the balloon altitude was higher than the intensity at the surface. So this was the discovery of the cosmic ray or cosmic radiation. With this, people realized that there are phenomena in the universe that cannot be observed with optical telescopes. In particular, people realized that these radiation are particles. Therefore, people had a question where and how these particles are accelerated in the universe. So this was the discovery of cosmic rays. And yes, in fact, the studies of cosmic rays became an important scientific field. And therefore, in Japan, Cosmic Ray Observatory of the University of Tokyo was established in 1953. And this observatory was later, in 1972, reformed to the Cosmic Ray Institute for Cosmic Ray Research of the University of Tokyo. So I'm belonging to this institute. Well, about 100 years ago, the study was, well, I would say this way. However, now in our institute, we study cosmic rays in various ways. In particular, here I show the map of the facilities related to our institute. We have we have a facility to observe the highest energy cosmic rays here in United States. And we have a gamma ray facility in La Palma, Spain. And we have Galactic Cosmic Ray Observatory in Tibet. And in Japan, we have Super Kamiokande Neutrino Facility and Kagura Gravitational Wave Facility. So, our studies of cosmic rays have been really expanded. And today, I'm going to talk about the neutrino studies and gravitational wave studies in our institute. Okay, now I want to talk about the neutrinos. Well, already there was an introduction, therefore I may not spend too much time for the introduction of the neutrinos. Anyway, this is the, say, one-page summary of neutrinos. Neutrinos are fundamental particles like electrons and quarks. And neutrinos are something like electrons, but without electric charge. And in fact, this feature had a significant consequence. Neutrinos can easily pass through even the Earth or even the Sun. And therefore, they can bring information of the fundamental processes at the center of the stars. In addition, I want to say that neutrinos have three types, or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And neutrinos have been assumed to have no mass. Okay, now we have to somehow study these neutrinos. how shall we study these neutrinos? Of course, we can never see neutrino itself. But fortunately, sometimes, although it's very rare, sometimes neutrino interact with the nucleus. And in this case, typically a charged particle is emitted. And in fact, we have various ways to observe this charged particle. For example, if the nucleus is a water nucleus, then this particle propagates in the water, and at that moment, photons or light are emitted by this particle. And of course, we can detect these photons by photodetectors. So this way, by observing photons, we understand that a neutrino interaction occurred at that moment. So this way, we study neutrinos. Okay, now I want to discuss Kamiokande. About 50 years ago, in the 70s, new theory of elementary particles called grand unified theories were emerged. And this theory predicted that protons should decay with the lifetime of about 10 to 30 years. Well, you can imagine how long the lifetime of proton is, 10 to 30 years. The age of the universe is about 14 billion years. So the predicted proton lifetime is much, much, much longer than the age of the universe. But of course, we know that if the proton lifetime is 10 to 30 years, in this case, if we observe 10 to 30 protons for a year, we should be able to observe one proton decay. So this is a trick. Therefore, people decided to search for proton decays, and these experiments began in various places in the world, and one of them was Kamiokande. And here I showed a sketch of the Kamiokande detector. It had about 16 meters in diameter and 60 meters high, and contained 3,000 tons of very clean water inside. And therefore, it contained a lot of protons inside. And therefore, some of the protons may decay while we watch inside the water. Well, you see there are many orange circles. They are actually the photodetectors to observe photons emitted by charged particles, and these particles are produced by proton decays. So this way, we wanted to observe proton decays. And the experiment was located here in the mountain area. And of course, we had to construct a detector. So in the spring of 1983, we came to this site. Actually, this was an active mine. We constructed this Kamiokande detector in an active mine. And here, you can see the people who contributed to the construction of the Kamiokande detector. And well, in front, you see Professor Koshiba, who was my thesis advisor, and also he was the leader of the Kamiokande experiment. And as introduced, Professor Koshiba received Nobel Prize in Physics in 2002 based on neutrino observation in Kamiokande. Well, okay. We have to construct a detector. In particular, we had to install the photodetectors onto the detector tank. Well, I said Kamiokande was 16 meters high. Therefore, we had to be careful to install these photodetectors safely. And the solution we adopted was to use this plastic board. Well, this way, we can install the photodetectors. Then, if we finish one row, then we raise the water level, then put another layer of photomultiplier or photodetectors onto the tank. So, well, this was not a very efficient way to install the photodetectors, but, well, we were safe. And in fact, I enjoyed these works very much. Also, I was excited because I thought that the data from Kamiokande may contribute to physics much. So around that time, actually, well, that was the first year in the PhD course, I decided to be a physicist. By the way, actually, this was me about 40 years ago. Okay. Anyway, of course, we wanted to observe proton decays. Unfortunately, we didn't observe proton decays. However, soon after the start of the experiment, we realized that the photodetector we used, this big one. Actually, this big phototube or photodetector was developed specially for this experiment. And we realized that this photodetector has a very good sensitivity. Therefore, by looking at the early Kamiokande data, Professor Koshiba proposed to observe solar neutrinos. Well, the sun is generating energy by nuclear fusion processes, and during these processes, neutrinos are created, and therefore, if we observe solar neutrinos, that is the direct study of the nuclear fusion processes in the sun. And anyway, Professor Koshiba proposed to study solar neutrinos in Kamiokande. And in fact, this was actually not easy. Compared with the proton decay signal, the solar neutrino signal is much weaker, about 100 times weaker. Therefore, the observation of solar neutrinos is not easy. However, Professor Koshiba realized this photomultiplier tube or photodetector is very powerful. Therefore, he thought it could be possible to observe solar neutrinos. Anyway, after this initial idea, people realized that we have to improve the original Kamiokande detector to observe solar neutrinos. So, in 1984, 85, 86, we spent a lot of time to improve the detector. And finally, after 3 years of improvement work, Kamiokande detector was ready to observe solar neutrinos at the beginning of 1987. Then something unexpected happened. In February 1987, there was a supernova explosion at the Large Magellanic Cloud. So these two photos are the Large Magellanic Cloud, and you see before and after. So at that moment, there was a very bright star, and this was the supernova explosion. And as I said, after 3 years of the improvement work, Kamiokande was ready to observe solar neutrinos. And in fact, the energy of the supernova neutrinos and solar neutrinos are similar, or supernova neutrinos a little bit higher compared with solar neutrino energy. And therefore, we thought that in the data collected in Kamiokande, there might be some evidence for the supernova neutrinos. And in fact, immediately we found a neutrino burst. Within 13 seconds, we observed 11 neutrino events. And this observation was confirmed by other experiments in United States and Soviet Union at that time. Anyway, the total number of neutrino events observed by these 3 detectors was only 24. But this was already enough to understand the basic mechanism of the supernova explosion. Namely, we understood that when a massive star finishes its life, the star collapses, then a shock wave is generated and the outside of the star explodes. So, by this contribution to physics and to astronomy, Professor Koshiba received Nobel Prize in Physics in 2002. Okay, now I want to change the topic to atmospheric neutrinos. Well, I said Kamiokande was the proton decay experiment. We wanted to observe proton decay. In order to observe proton decays, we have to understand the background. That is the atmospheric neutrinos. And these neutrinos are created by cosmic ray interactions in the atmosphere. Cosmic rays are high energy particles coming to the Earth, and they interact with the air nucleus, typically producing pions. Of course, pions are unstable, decay to muon. And muon is again unstable, decay to an electron. So during this decay chain, neutrinos are created. So we thought we have to understand this neutrino background. And around 1986, we thought we have to improve the proton decay analysis in order to better separate the proton decay signal and background. So I developed a new software to improve the proton decay analysis. And accidentally, I noticed that the event rate of the atmospheric muon neutrinos was much lower than expected. Well, initially, I, of course, thought that this was my mistake. So I thought I have to find out the mistake as soon as possible. Well, unfortunately, I studied hard, but I didn't find any simple mistake. I studied what was my mistake for a year, but still I didn't observe any, I didn't find any mistake. So eventually, I was essentially convinced that the deficit of mu neutrino was real. So we decided to publish our data in a scientific paper. In fact, this paper was quite simple in a sense. We simply reported the number of observed mu neutrino events, which was 85, and compared with the expectation, that was more than 140. So clearly, data showed a large deficit. And also, we counted the number of electron neutrino events, and we found that for electron neutrinos, the data and the expectation agreed reasonably well. So this was our conclusion. We simply concluded in this paper that we do not understand. Anyway, we had no clear idea what was the cause of the deficit, but I was most excited with the data. So I changed my research from proton decay searches to neutrino studies. And of course, I wanted to find out what was the reason for the deficit. Well, there could be several possibilities. And, well, in fact, one of the possibilities we thought was neutrino oscillations. Well, actually, the neutrino oscillation was predicted more than 50 years ago by Maki, Nakagawa, Sakata, and Pontecorvo. Anyway, according to them, if neutrinos have mass, neutrinos change their type from one type to the other. For example, a mu neutrino may oscillate to tau neutrinos. So for example, if a mu neutrino is created at this point and begin to propagate to right, then at some point, this neutrino changes to a tau neutrino. But if they propagate further, that neutrino type come back to mu neutrino. So this way, neutrino type changes as they fly. So this was neutrino oscillations. And if this is happening, then one can naturally explain the deficit of mu neutrinos. Well, okay, this was one of the possibilities to explain the deficit of mu neutrinos. And therefore, we wanted to know if neutrino oscillations is the real reason for the deficit of mu neutrinos. And for this, we wanted to positively identify neutrino oscillations. And for this, we thought this way. As I said, neutrinos are created by cosmic ray interactions in the atmosphere. Therefore, some of these neutrinos are created above the Kamiokande detector, say 10 to 20 kilometers above the detector. And they come to the detector after 10 to 20 kilometers. then these neutrinos may have no time to oscillate because the flight length is short. And these neutrinos are also created in the other side of the Earth. And they have to travel a long distance before interacting in the Kamiokande detector. So these neutrinos created in the other side of the Earth may have enough time to oscillate. So if we think this way, we thought that we should observe the up versus down asymmetry of the atomic mu neutrinos. However, Kamiokande 3,000-ton detector was too small to observe this effect, so we needed Super Kamiokande. And Super Kamiokande is a much larger version of the original Kamiokande detector. It is a 50,000-ton water Cherenkov detector. It has about 40 meters in diameter and 40 meters in height. And the inside of the detector looks like this. And well, you see something here. And this is a plastic boat with 3 people on it. So you see the detector is really big. And well, experiment started in April 1996. And from the beginning, the detector worked quite well. And after 2 years of the experiment, we were able to get a rather strong conclusion. And here I want to show you our data that were presented at the Neutrino Conference in 1998. Here I show a zenith angle distribution of muon neutrinos, and 1 means downgoing neutrinos, -1 means upward-going neutrinos. They come from the other side of the Earth. And these black circles with error bars show the data, and these hatched histograms show the simulation expectation. So by looking at this graph, you find for downgoing neutrinos, the data and the simulation or expectation agree quite well. But for upward-going neutrinos, the data showed essentially a factor of 2 deficit. And this can be, of course, well explained if neutrinos oscillate. And this way, we were able to convince the world neutrino community that neutrinos oscillate, and that means neutrinos have small mass. Of course, we presented our result at the conference for physicists. Then, unexpected happened. President Clinton of the United States of America gave a talk at MIT's 1998 commencement. Well, in his talk, he mentioned about the discovery of neutrino oscillations. Well, of course, that whole talk is 30 minutes long, and therefore I pick up the part related to the discovery of neutrino oscillations. And he said, just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories, from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. Of course, as the US president, he mentioned the US contribution to Super Kamiokande. Then he continued, the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So, well, it was really an honor for us to hear this kind of statement on the next day of our discovery announcement. By the way, you may ask, why the discovery of neutrino mass is so important? Well, of course, electrons have mass, quarks have mass. Then maybe it's natural that neutrinos have mass. Well, actually, we still think that neutrino mass is very important. And I want to convince you that indeed neutrino mass is important. Here, I show the mass of charged leptons, electrons, muons, tau. The charged lepton mass is shown by red, and quark mass is shown by green and blue colors. Now, after 25 years of studies of neutrino mass by the world community, we understand the neutrino mass rather well. And they are about this value, these values. So you find that neutrino mass is very small. Well, you have to be careful about the horizontal axis. Anyway, from this figure, we can easily find that neutrino mass is approximately, or maybe more than, 10 billion times smaller than the corresponding mass of quarks and charged leptons. 10 billion times smaller, 10 orders of magnitude smaller, very small, extremely small. And we believe this is the key to better understand elementary particles and the universe. Therefore, we are excited with the neutrino mass. Of course, if we understand why neutrino mass are so small, then certainly I think we better understand elementary particles. But also we think neutrino mass is very important for the understanding of the universe. Why? Well, this is a photo of the far universe taken by the Subaru telescope. And you see many galaxies. And these galaxies are made of matter. We know that there is no antimatter galaxy. Well, this seems to be so trivial. However, if we think about the Big Bang universe, we realize that we cannot understand why the present-day universe has matter only. Well, in fact, in the Big Bang universe, the temperature was so high, therefore, in the Big Bang universe, always matter and antimatter particles were created simultaneously. Therefore, in the Big Bang universe, the number of matter particles and antimatter particles should have been equal. Then, with the universe cooled down, matter and antimatter particles meet and annihilate. So, naively, we expect at present the universe, we should see nothing. Of course, we know that there are matter particles in the present-day universe. Why? Well, in a sense, we understand. In the Big Bang universe, there were, say, 1,000,000,001 matter particles and 1,000,000,000 antimatter particles. They were almost equal. Then, with the universe cooled down, they meet and annihilate, and therefore this extra one remains in the present-day universe, and they are us. So this way we understand. However, of course, we have to understand why there was extra one in the matter side of the early matter side in the early universe. In fact, there is a proposal, theoretical idea that neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. Well, if there is a theoretical idea, we should check as much as we can. Certainly, this is a very important question to really understand our existence in the universe. So, now in the neutrino community, people are very serious in understanding the origin of the matter in the universe. And in fact, we would like to observe if oscillation of neutrinos and those of antineutrinos are different. If the difference is observed, it will be the first step to understand origin of the matter in the universe. And for this, Hyper-Kamiokande detector is under construction. Hyper-Kamiokande will be a next generation neutrino experiment. It will be about 8 times larger in the mass. And we expect the experiment will start in 2027. That is about 4 years later. And this is, in fact, a very large international collaboration. In this experiment, there are more than 500 people from 21 countries and regions. So, I'm looking forward to seeing the result from this experiment in the near future. Okay, now I want to move on to a completely different topic, that is gravitational waves. In fact, in the last 15 years or so, I have been working on gravitational waves. And before talking about the gravitational waves, I briefly want to discuss why I am now working on gravitational waves. Well, as I said, I worked in Kamiokande and Super Kamiokande. And I was fortunate. I was able to be involved in the discovery of neutrino oscillations. However, around 2005 or 6, I thought I finished what I should do with the neutrinos. And I wanted to do something new and exciting. And therefore, I decided to work on gravitational waves. Anyway, let me discuss what are gravitational waves. Well, gravitational waves were predicted by Albert Einstein in 1916 based on his theory of general relativity. And we expect that a strong gravitational wave is emitted by a merger of binary black holes. For example, let me show you this video. So you see there are two black holes orbiting each other. Well, they emit gravitational waves, and therefore they come closer and closer, and finally they come very close, and okay, then these two black holes merge at this point. Then a heavy black hole is created at that moment. And then if we look at the outer space, we find that the gravitational wave is propagating to the outer space. So this is the gravitational wave. Then you may ask how we should observe these gravitational waves. Well, we use a simple technology, laser interferometer. Here is the laser, and here is the beam splitter. Half of the beam pass through and go to the mirror there, and the light come back. And half of the light is reflected here and go to this mirror and reflected back. And then these two lights interfere. And of course, I would like to show you by video. Now, if the mirror moves, then intensity of the interference light changes. So typically, it is tuned that the interference light is minimum. But if the position of the mirror changes by some reason, then the interference light intensity change. So this way, we can observe gravitational waves. Now, I want to discuss what we would like to know by observing gravitational waves. Well, here I showed the main targets of the present generation gravitational wave detectors. And the first target is the merger of binary neutron stars. Well, you may know, neutron stars are compact but extremely heavy objects. They have typically, say, diameter of 24, 25 kilometers, but the total mass of a single neutron star is about 1.4 solar mass, so very heavy. Anyway, there should be some system, binary system of binary neutron stars, and with by the emission of the gravitational waves, these neutron stars eventually merge. And at that time, we think that heavy metals are generated. heavy metals means gold or platinum. So, actually, other than this, we do not know how to generate platinum, gold in the universe. So we really want to understand the origin of the heavy metals in the universe. Furthermore, we want to understand neutron stars better. Well, neutron stars are very special stars, so we want to understand these stars very precisely. Another target is the merger of binary black holes. And in fact, as I discuss later, so far there have been many observations of binary black holes, and we found that we do not understand the origin of these black holes. They are rather heavy. We'd like to understand the origin of these heavy black holes. And finally, we'd like to understand the supernova explosion by observing the gravitational waves. So we have a lot of important science with the gravitational wave astronomy. So we'd like to study gravitational waves. And in fact, already 8 years ago, on September 14th, 2015, the LIGO project in United States observed signals in their 2 laser interferometers. And the data are shown here. You see there are 2 curves, one orange, one blue, and they agree very well. And they are the data from these 2 laser interferometers. And the data told us that 2 black holes of 36 solar mass and 29 solar mass merged at a distance of about 410 megaparsec, newly forming a 62 solar mass black hole. We think this was really a great discovery. The gravitational wave astronomy was born. Well, that was 8 years ago. The observation is continuing, and so far, about 90 gravitational wave events have been observed. And people are really excited with these observations. Therefore, we'd like to contribute to the gravitational wave astronomy with the KAGRA gravitational wave project. KAGRA is an international collaboration. We have about 150 authors of scientific papers. They come from 8 countries and regions. And you see that these are mainly the East Asian countries and regions. And also I want to say that Taiwan is the 2nd largest group in the KAGRA collaboration. Anyway, KAGRA is another large laser interferometer. It is located underground. It has 3 kilometer by 3 kilometer arm length. And in fact, KAGRA has 2 key features. Well, other laser interferometers in United States and Europe, they are located at the surface. but the Kagura interferometer is located in underground. In fact, we think underground site is very important because the seismic activity is much smaller. In addition, we use cryogenic mirrors. Well, actually, this kind of laser interferometer must be extremely sensitive. Therefore, at the end, the thermal noises of the mirror could be a problem. So we decided to cool down the main mirrors to 20 Kelvin. Anyway, the project was approved in 2010, and since then we have been constructing the interferometer. And about 4.5 years later, after the approval, the tunnel was excavated and the 3-kilometer vacuum tube was installed. So this is one arm and this is another arm. Then, of course, we have to install the cryogenic mirrors. This is one of the cryogenic mirrors, and this is in fact a sapphire mirror. It has a 22 centimeter in diameter and 15 centimeter in thickness. The weight is 23 kilograms. And this photo was taken during the preparation of the mirror. Then later, this mirror was brought into the Kagura site underground and installed here. Anyway, the experimental site is rather complicated. This is the central area, and you see here is vacuum tank, and in this vacuum tank, beam splitter is located, and also you see beam tubes. So this is the most complicated part of this experiment. Also, the laser system is complicated. This is the laser room that produces high power, high quality laser light, and this light will be injected into the Kagura laser interferometer. So, in the initial 9 years or so, we have been constructing the interferometer. And finally, we were ready to start the commissioning of the laser interferometer. After finishing the construction of the laser interferometer, every work is by computers. So this is the photo of the Kagura control room, and here people remotely operate the laser interferometer. And well, I would like to briefly tell you what we have done in the Kagura commissioning. We'd like to achieve high sensitivity. And here shows the history of the Kagura sensitivity improvement. The horizontal axis is the frequency, hopefully of the gravitational wave. Then here is the say sensitivity. And if you go down, then I would say this is actually a noise curve. Therefore, if you go down, then you have smaller noise, therefore you have higher sensitivity. And this is the design sensitivity of Kagura. And well, we have been improving significantly. In particular, this blue curve was taken in August 2019. Then with less than a year, in March 2020, we improved this way. So you find that more than 3 orders of magnitude improvement in sensitivity in less than a year. Anyway, at that point, we thought we should do our observation. Unfortunately, due to COVID-19, we stopped the observation in 2 weeks and started the detector improvement work. And after that, for the last 3 years, we worked for the improvement of the Kagura laser interferometer. Okay, I briefly discussed what we are doing in Kagura. Now, coming back to the science, we know that scientific output will be maximized by the global network. That means if we work together, Kagura, LIGO, Virgo, the scientific output will be maximized. For example, in order to do gravitational wave astronomy, we have to tell astronomers, optical astronomers, where is the event occurring, which direction. Therefore, we have to be sensitive to the direction of these gravitational wave events. And the pointing accuracy of the gravitational wave events will be much improved by the network of these global LIGO, Virgo, Kagura detectors. And in fact, the observation with LIGO and Virgo started on May 24 this year, about a week ago. And Kagura joined the observation. So this is really an exciting moment for us. And we'd like to contribute to the gravitational wave astronomy through Kagura. Well, today I first discussed neutrinos, then I discussed gravitational waves. Well, I separated these two topics. However, I want to tell you that at some point we work together, neutrinos and gravitational waves. For example, if a supernova explodes at the center of the Milky Way galaxy, then we'd like to observe gravitational waves emitted by the supernova explosion. Also, at the same time, we expect that neutrinos will be detected by the neutrino detectors. And we think that we can truly understand the mechanism of the supernova explosion by combining data from gravitational waves and neutrinos. So, although I discussed neutrinos and gravitational waves separately, it's very important to work together, neutrinos and gravitational waves. Okay, let me summarize. Neutrinos and gravitational waves are exciting scientific fields, and I think I was lucky that I was able to work on these research topics. And we expect many more fundamental discoveries will be ahead of us. And also, I want to point out that in order to maximize the scientific output, we collaborate with many people from various countries and regions. It's very nice to become friends through these collaborations. So, my final message is, let's enjoy science together. Okay, that's all. Thank you very much for your attention.
Sincerely thanks to Professor Takaaki Kajita for his speech today. Now we are going to have Q&A session. Teachers and students are welcome to ask questions. 感谢尾田龙章教授今天带来的演讲。现在是 Q&A 时间，欢迎老师及同学们踊跃发问。
Thank you for the speech. So back then when you first proposed the project of Kagura, do you have the confidence that we must have the detection on the gravitational waves, given at that time we don't have any detection?
Yeah, thank you very much. Well, certainly we needed the help from the theoretical community. There have been many studies on the, say, expected event rate of the neutron star mergers. And well, before the actual discovery, people had a rather good idea the event rate of these neutron star mergers. And therefore, we had say, good idea about the event rate of the neutron star mergers with the 3 kilometer by 3 kilometer laser interferometer. And in fact, 3 kilometer by 3 kilometer laser interferometer was the kind of minimum configuration to really observe these events. And as I said, in fact, 3 or 4 kilometer laser interferometers already observed 90 gravitational wave events. This was essentially expected.
I see. And actually different from LIGO's and Virgo's design, there are many new technologies used in Kagura, especially cryogenic. So I heard people yesterday in the international workshop, there are some doubts on the extra noise brought by this kind of cryogenic system. So yeah, because we are working on reducing the noise of Kagura too. So may I ask initially why we must introduce such a system?
Okay, thank you. Well, first of all, as you may know, Kagura started later compared with LIGO and Virgo. Compared with LIGO, we are, say, 20 years behind. And already when we designed Kagura, we knew that eventually thermal noises of the mirrors and suspensions would be a problem. Therefore, as a project that started late, we decided to reduce these fundamental noises by a new technique, cryogenics. Of course, we realized it's not easy. There could be extra noises introduced by using the cryogenic system. But, well, I believe our colleagues have been careful enough not to introduce extra noise. Therefore, finally, we could have an advantage of the cryogenic system.
Okay, thank you very much.
So, hello. Well, the construction of hypercamioca produce like side effects to the data in Kagura, and another question is also that why is the detection of antineutrinos can help to solve this baryon number asymmetry?
Oh, okay. First is the interference of the hypercamiocan construction to Kagura. Yes, we worried about this possibility. Therefore, hypercamiocande is actually constructed in a different mountain, 8 kilometers away. So we hope the interference of the construction of hypercamiocande will be minimum. And
Yeah, but I believe that will still cause a very huge influence. Yeah.
I hope not.
Yeah, we all hope not.
In particular, there could be two possible noise sources with the construction of the underground cavity. One is the explosion, explosives. The other is the traffic of the construction. And explosive is only for a short time. Therefore, this may not be a real serious problem. On the other hand, traffic could be a serious problem. And, I'm sure this cannot be a problem 8 kilometers away. But I forgot about your second question.
Oh, the second question is... Hello. Okay, so the second question is that antineutrino, how can the detection of antineutrino help to solve this baryon number asymmetry?
Okay, thank you. This basic idea is in the nature, there could be some asymmetry in the law related to particles and antiparticles. This asymmetry is called CP asymmetry. And so we'd like to convince that neutrino physics, there is also some difference in the fundamental law in particles and neutrinos and antineutrinos. And for this, we'd like to observe the oscillation difference between neutrinos and antineutrinos. And hyper-K is constructed for this purpose.
Thank you very much for the very nice talk. I have a question about design sensitivity of Kagura, because as we can see that now the observation are by combining several laboratories, LIGO, Virgo. So is it really worthwhile or necessary for Kagura to go to the design sensitivity? Because now it does not operate alone independently.
Oh, okay, thank you. In fact, we think it's really important to achieve the design sensitivity as soon as possible. Well, although I say as soon as possible, it may be, say, 5 years later. But anyway, I think it's really important because we'd like to have a good pointing accuracy of the gravitational wave events. And for this, it's really important to have at least 3 laser interferometers on the Earth. And we hope that these 3 interferometers are far away each other. And therefore, Kagura is really important to have a good sensitivity. And if Kagura does not have a good sensitivity, then we know that for some sources, the pointing accuracy by LIGO and Virgo only are rather poor. So we really think Kagura is very important, and therefore we have to achieve the high sensitivity as soon as possible.
Thank you very much.
Thank you for giving us a nice lecture. I have a question. Can we have another way to measure the gravitation wave without using the lasers? Because the laser is invented roughly in the 1960s. Yeah.
Thank you. Thank you for this question. Well, if we look back the history, there was another type of the gravitational wave detector. For example, they used a very heavy mass, and if a gravitational wave hit this very heavy mass, then there must be some excitation of this big material. Therefore, they would like to observe this small excitation on this big material. But people realized they cannot achieve a high sensitivity. And as far as I know, at this moment, the only technology we have is the laser interferometer.
Thank you.
Thank you, very nice lecture. In the example of the collision of two black holes that you talk about, there was a deficit of 3 units of mass, I think. Did it go all to radiation, all to the gravitational radiation, or there was also electromagnetic burst accompanying this?
Thank you. Yes, we believe all these 3 solar mass equivalent was changed to the energy of the gravitational wave. And so far, we have no evidence of the electromagnetic radiation at that moment. But, well, maybe in the future, we should study more to check if there's really no electromagnetic radiation.
Thank you. And one more question. So the gravitational waves are the wave character of gravity. But is there any research going into detection of gravitons, corpuscular part of that?
Okay, thank you. Well, actually, I'm not an expert on this topic, but as far as I understand, there's no idea to really observe gravitons.
Very impressive talk. So I have a very naive question. How often, like, this gravitational wave comes to Earth, and is it possible to see, to observe the superposition of 2 events if they happen together? The superposition.
How often the gravitational wave come to the Earth?
Yes, and the superposition of 2 gravitational wave.
Well, yes, okay, thank you. Well, okay, the answer to the first question, how often, depends on the strength of the gravitational waves. For example, the strong gravitational waves, which can be detected by the present-day detectors, the rate they come to the Earth could be, say, 1 event per week. However, of course, much weaker gravitational waves come more frequently, and certainly there could be a possibility that two completely independent gravitational waves come together at the moment.
Thank you very much for the talk. You showed this nice plot about the neutrinos, where you had the electron neutrinos and the simulation, and it agreed nicely. And then the muon neutrinos, where you had a difference, which basically means they were tauan neutrinos, so you had oscillations from muons to tauans. Now my question is, would it also be possible somehow to detect tauan neutrinos directly, or what is the difficulty here?
Thank you. It's in fact a very good question. Okay, there are in fact several difficulties to observe tau neutrinos. First of all, in order for a tau neutrino to interact with the nucleus, they have to produce tau lepton, but tau lepton is heavy. Therefore, in order to produce tau lepton, the neutrino, tau neutrino must be energetic enough. And therefore, we naively expect that the tau neutrino interaction should be low, interaction rate should be low. Furthermore, the tau lepton, produced tau lepton, almost immediately decay to other particle within, say, less than 1 millimeter of light. And therefore, we have to somehow identify the evidence for tau particle. This is not easy. Anyway, it is possible to observe the tau neutrinos created by neutrino oscillations. And so far, actually including Super Kamiokande, the world community have already good enough evidence that tau neutrinos are created by neutrino oscillations by directly observing charge current nu tau interactions. I mean, tau lepton by observing the tau lepton creation.
Thank you.
Thank you for your introduction to the knowledge. I'm curious about how can we distinguish the signals in the whether the signal is from the upside or downside.
Oh, okay, thank you. Maybe, okay, well, at the beginning, I showed this, and in fact, these photons emitted by this charged particle has the directionality. If a particle propagates this way, then these photons are emitted in the rather forward direction. Therefore, by observing this ring pattern, you can know how the particle propagate in the water, and therefore, by observing this particle direction, then you know the rough approximate direction of the neutrino direction.
Thank you.
Thank you for your amazing talk. I have a question. It's about the gravitational wave. Just that we know that the gravitational wave is generated by two massive black holes, and how could we know their mass for each other?
Thank you. Okay, for this, we need the help from the theoretical simulation. Anyway, the point is, if the mass of the black holes are heavy, then the frequency of the gravitational waves are lower. If the black hole mass is small, then the frequency is higher, and this way we can estimate the mass of these black holes.
Thank you.
So, if I may ask a question that's not related to gravitational waves or neutrino. In your opinion, do you think it's still worth searching for proton decays, as you mentioned it?
Okay, thank you. Well, okay. Yes, my answer is yes. Well, the idea of grand unification of elementary particle forces is very, very attractive to physicists. And even now, we believe the observation of the proton decays is really the direct evidence for the unification of the forces. Therefore, we should try to observe proton decays as much as we can. And in fact, I hope that hyper K, which is a very sensitive proton, in fact, it's going to be a very sensitive proton decay experiment. So I hope to see the results from hyper K.
Yes, I have a question. Originally, in the Camille Candé, and because we want to try to detect the proton decay, so we use water as a media because it contains a lot of proton, right? But when we want to detect the neutrino, why we still choose the same media, not choose another maybe better media to to detect the neutrino?
Okay, thank you very much for this question. Well, okay, neutrino interactions are very rare. Therefore, in order to observe many neutrino interactions, we need a large target mass. Now, if you think about the cost to prepare the large mass, you find water could be the cheapest. Yeah.
Thank you.
Thank you for your speech. Is there any quantum perspective of the gravitational wave?
I have no idea, sorry.
Thank you.
Kajira Sensei, thank you for your talk. I have a relatively non-relevant question. Has anyone actually fallen into this water tank when they're on this plastic boat?
Fall into the water tank while working?
Yeah, working on the setup of the...
Yeah.
Well,
okay.
Because you mentioned the waters should be very clean, right?
Yeah,
so
yeah.
if someone is actually falling into it?
Well, in the history of the Kamiokande and Super Kamiokande, several people dropped into the water. Yes.
Thank you.
Yeah.
好，因为时间缘故，那今天的 Q&A 就先到这边。然后 in the end, let's invite Vice President Chen Yongfu to present a souvenir to our speaker. And once again, thanks to Professor Takagi Gajita for coming to our school to give the speech. 恭请
Thank you. Thank you.
现在请各位老师到台上进行合照。